I have been given the instruction that we can start. Distinguished guests, ladies and gentlemen, good evening and welcome. The last time I was in this wonderful venue, I was chairing a meeting of Senate because I'm Loyiso Nongqa and I'm the Vice Chancellor and Principal of the University. Now, one of the big questions I was asked when I announced that next year WITS will be celebrating its 90th anniversary. And we should think of themes with the number 90 to celebrate 90 years. One senior professor seated at the back, he said that, Vice Chancellor, please get us 90 parking lots. So I hope that you didn't struggle to find parking outside. It's a privilege for me to welcome all of you to this evening's event. Special word of welcome to the guest speaker, Mr. Philippe Pelnik, who will be introduced by the president of the institute. Mr. Pelnik is from Alstom, the Paris office. Special word of welcome to Mr. Andries Chabalala, who's the president of the South African Institute of Electrical Engineers. And also welcome back to the members of the Institute of Electrical Engineers, and I see quite a number of familiar faces. Now, this is the, I'd like to extend a special word of welcome to members of the Bernard Price family. Roger, Angela, and Christopher Price. Those are the names that I was given. Maybe some of them are here. Now, if you drive up Jubilee Road, just past the temple, number 13, you won't see the house there. It's a beautiful house if they allow you to move inside the gates. It's called Savanak. It used to belong to the Bernard Price family. And the current tenant is the Vice Chancellor of this university. I also want to welcome all the members of the university community, academics, support staff, as well as the students. This is the 60th Bernard Price lecture taking place at our university. I know that the guest speaker has been to other centers already, Cape Town, Durban, and George. But this is the Bernard Price lecture, not the ones that he gave in Durban. I've been at this university for about 11 years, 8 years of them, and I'm counting as Vice Chancellor. And I've always had this privilege of welcoming people to this lecture. And I always give different speeches. Those of you who have attended them, you can check if I'm saying the same thing I said last year and the year before. Now, it's one of the highlights of our academic calendar to have members of the profession, members of the university community, and listening to a distinguished speaker, guest speaker, talking about issues that are important not only to the electrical engineers, but to all of us. Dr. Bernard Price was an amazing man. And as far as this university is concerned, he has left a lasting legacy. When I arrived here, there were 2 institutes named after him, the Bernard Price Institute for Geophysics, and there's the Bernard Price Institute for Paleontology. And of course, I've already pointed out that through the Price Trust, their generosity, that a Vice Chancellor of this university has to give up his own house and go and live in that wonderful house. Now, to commemorate his name, the Institute's Council decided that there should be an annual lecture to be known as the Bernard Price Memorial Lecture, and as I've already pointed out, this is the 60th such lecture taking place at this university. The lecture is always given in recognition, amongst others, of the work that Dr. Bernard Price made possible. And it is to commemorate a very great scientist who developed the electrical industry in South Africa. Once again, welcome to this special lecture, and I'll now invite the president of the institute to introduce the guest speaker. Thank you.
Professor Nongqa and staff of the university, members of Council of the South African Institute of Electrical Engineers, members and their guests, and ladies and gentlemen, good evening. It is great to be here tonight in memory of this great giant in the history of science and engineering in South Africa. Indeed, Prof, we feel welcome at this institution. Tonight, we have the 60th Bernard Price Memorial Lecturer as Mr. Philippe Parling, who has agreed to come and deliver this 60th lecture of this series of lectures. As the Prof has said, my name is Andries Shabalala, the current president of the Institute. Not belonging to the rich Shabalalas, but one of the poor ones. There's quite a few of them in Soweto who has got some cash. My immediate duty is to introduce the speaker tonight. Mr. Philippe Parling is a director of CO2 Systems Business Development and is based in the headquarters of Alstom in Paris, Levallois. Philippe supports technically and commercially the global power sales, at Alstom they call it GPS sometimes, and marketing organization in order to promote upstream CO2 capture solutions to the market. He is interfacing with Alstom's power business, R&D, sales, and all market players in CO2 related issues. Philippe also strongly contributes to the key messaging of all Alstom CO2 related communications. Philippe has an extensive sales and technical background with UOP, a worldwide market leader in refining and petrochemical process licensing. He held several managerial positions in Europe relating to fluid purification processes and products. Philippe is a chemical engineer. When you mention that, some people say it's shame. He's a chemical engineer from the ISIB Brussels and holds an MBA from the Erasmus Rotterdam and Rochester universities in New York. Philippe is co-leader of the task force demonstrations and implementation of the European Zero Emission Platform, ZEP. He is an authorized speaker to present Alstom CO2 abatement technologies and strategy to external audiences. Having a good expertise on those subjects, he is frequently invited in international events and seminars as panelist or guest speaker. The presentation is headed Carbon Capture and Storage, Ready to Deliver. The presentation will deliver a brief history of development of the technology, the various capture technology choices and trade-offs, the main pilots worldwide, the results of main demonstrations, the costs of CCS, carbon capture and storage, and the remaining challenges to reach commercial stage. Ladies and gentlemen, please put your hands together and welcome our speaker tonight.
Thank you, Andries. And yes, Mr. Vice Chancellor, this is the evening because it's the first time where I'm wearing my tie to give my presentation. So, you have a chemical engineer to address an audience of electrical engineers or to-be electrical engineers. And this is all happening in the School of Accounting. So, but I hope by the time I finish my presentation, you will be convinced that accounting is relevant. We have to account for our carbon footprint. And you will also see that science and technology is getting more and more integrated. And now has the time come where electricity production needs the help of chemical processing to get rid in a safe way of the carbon emissions. I propose to cover the following agenda. First, a few slides to remember you what is Alstom, what we are doing in general as an equipment supplier. We will then cover the climate issue and see how it relates to power production and what we can do. We will cover the carbon capture and storage technology choices. I will show you a couple of roadmaps of our own product development. We will then see the results that we have already obtained from our pilot work, and we will also address the issue of the cost of carbon capture and storage. I will be briefly speaking about CCS ready. How can we make a power plant ready to capture tomorrow when this will be needed? I'll talk about the status of the deployment of the technology, and then I'll touch briefly on the policy arena, the expectations we may have for the COP17 that is going to take place in Durban later this year. Let's start with Alstom. So we are a big international group and we supply equipment for power production, power transmission, and also equipment for rail transportation, those fast trains, metro and tramways. Some numbers about our company. We employ close to 100,000 people worldwide in 70 countries, and our total turnover is close to 21 billion euro on a yearly basis. You see a split between our different businesses. But the power business really is 3/4 of our turnover. We are a rather big employer here in South Africa. We have over 700 permanent employees that may fluctuate a lot with execution of projects. We are currently working on the Medupi and Kusile new coal-fired power plants, and we have been supplying equipment for 12 out of the 13 installed coal plants here in this country. And we've also participated in the equipment of the nuclear power plant. We are a supplier of what we call the conventional parts, so the big steam turbines and generators for nuclear power plants. The climate issue. First, a quick reminder slide about what we are talking about. Greenhouse gas, the greenhouse gas effect. It's about this effect where we have gases in the atmosphere like CO2, but water vapor that ensure that the warmth that we get from the sun remains on Earth. And thanks to those gases, we have an average Earth surface temperature of about 15 degrees, and we've been enjoying that for the last several million years. What is happening today is that since the beginning of the industrial ages, we are using a lot of fossil fuels and releasing massive amounts of carbon in the atmosphere. And that is progressively causing an imbalance and an accumulation of CO2 in the atmosphere. And this is what we would call the enhanced greenhouse gas effect. And we have started to see an acceleration of temperature increase. We are already 0.8 degrees above the average Earth surface temperature that existed before industrial ages. The consequences of a global warming or temperature increase have been described by the International Panel for Climate Change. And you've probably heard about this 2 degrees threshold that was at the heart of the Copenhagen Accord that was signed 2 years ago. We mustn't go above a 2 degree Earth surface temperature increase because those are the risks that we will be facing. The biggest one is water shortage. An increased average Earth surface temperature will put billions of people at risk. If we go above 2 degrees, it's about half of the planet will be suffering from water shortage in any of its forms. Going with this, increased risks of diseases and, of course, risk of hunger, also linked with water shortage. So, in order to avoid those risks, decision has been made by governments to try every effort to limit the global warming to less than 2 degrees Celsius. The context is, however, a context of increased energy demand linked to a growing population worldwide. And those are the numbers from the International Energy Agency, showing you the energy demand increase. We see strong increase in China, but also in the rest of the world and all developing countries. The only stagnation is in the developed countries, where we, however, manage to keep the same energy level. Of course, this is adding, these are the million tons of oil equivalent. This is adding to the fossil fuel emissions a big time between now and 2035. The consequence is that our CO2 emissions are growing. What this graph is showing on the left side is emissions expressed in gigatons. That's billions of tons of CO2 every year. We have reached and we have surpassed today a level of 30 gigatons of emissions every year. To give you a picture of what this means, 1 gigaton in the gas phase of CO2 is a bubble that is 10 kilometers in diameter. And we are flying 30 of those balloons every year. You see the acceleration since the end of the Second World War. So that's really when industrial ages have been taking off. Now, a lot of those emissions are coming from the power sector. That's from coal-fired or gas-fired power generation mainly. You see, and that's over 40% of the emissions. A big 20% from transportation, industry, residential, and others. So the power sector is probably the first place to attack CO2 emissions, because we have there large emissions in a concentrated form. And I'm going to detail you the potential solution to cope with that. Now, when we speak about climate change and CO2 accumulation in the atmosphere, we have to understand that coping with CO2 emission is not going to buy us a guarantee that we won't exceed the 2 degrees Celsius. Today, we already have 380 ppm, so that's parts per million, of CO2 present in the atmosphere. That concentration is increasing by 2 ppm every year. That's if we do nothing, we are going to accumulate and elevate this concentration in the atmosphere. Should we be able to stop the accumulation of CO2 to the atmosphere to a level of 400 ppm, we would still have 26% chance of exceeding this 2 degree Celsius temperature augmentation. The goal that is generally accepted, that we are aiming for, is the 450 ppm. And I'm going to show you what this means. And that would buy us only a 50% chance of not exceeding this 2 degrees Celsius. Now, if we let the emissions go beyond, God knows what will happen, but we will be facing probably much higher temperatures. Now, to achieve a 450 ppm scenario, those are the curves set by the IEA. We are today, as I said, at a level of 380. Those are the emissions in gigatons, 30 gigatons per year of emissions. We need to curve that in a very, very drastic way. So that's the minus 80% emission reduction that we need on a worldwide basis as soon as possible. The more we delay the effort, and you see already between the World Energy Outlook 2009 and 2010, the difference in the shape of those curves. If we delay, it means that we have to do more later on and faster. And that's something we probably want to avoid, but the time window to act is closing, and it's closing very fast. So what are the levers we can play with? That's a famous wedge analysis that was for which the IEA came up with recommendations. A first lever is efficiency. We must do more with less. That's very clear. And that is going to account for half of the reduction path. We have to use more renewables for energy production. We can use biofuels, nuclear is there, and CCS, carbon capture and storage, is also in the map and would account for 20% of the effort. So 1/5 of the reduction effort coming from CCS. It's not a matter of doing renewables or CCS, doing biofuels or nuclear. It's a matter of and. We need all those solutions. It's about a portfolio and a drastic one. When we talk about deploying CCS, 2035, it's avoiding about 4 gigatons of emission. We are talking about deploying more than 3,000 coal-fired plants, or deploying capture on 3,000 coal-fired plants. A gigantic effort. Pipeline deployment equivalent to the current gas industry worldwide. That's what we're talking about. Renewables, same way. It's a big deployment, much faster than what we are doing today. So we need all those things together and happening rapidly. The global context for power equipment is mainly a context where fossil fuels are still present for new installation and accounting for about close to half of the new equipment, but we see a clear trend of renewables coming in, and we have very strong equipment sales worldwide for renewables. The second main trend is that most of this equipment is being sold to Asia, and that's representing already 60% of our market. I have a more detailed view of those markets here. That shows you the size of the bubble, shows you the relative proportion of new equipment that is going to be installed over the 5 next years. And we will be seeing an average comprised between 200 and 250 gigawatts of new equipment being installed every year over the next 5 years. You see a lot of this equipment is going to go to China. The color code red stands for steam plants, or coal-fired power plants. The dark blue is gas. And then you see a big gas bubble in North America, Europe. A lot less coal has disappeared from the North American map. But what you see also is all those other decarbonized power solutions. In white, you have wind. You have in pale blue, hydro. And then the solar solution is this little orange that is already quite present in Europe. So about half of the new installations are going to go to carbon-free, but still a strong fossil fuel, and we need to have solutions for this. The approach of an equipment supplier like Alstom, but we've seen that for our competitors, obviously, is to increase its offering in those solutions that do not emit carbon. And we have, over the last 5 years, made an acquisition to be present in wind. We are developing a solution to harness power from ocean currents. We have revived a division we have on geothermal, and we have now a center in Mexico that is providing geothermal solutions. We have also accelerated our R&D and offering in biomass, and you can co-combust biomass in existing coal-fired plants, and it's a very good solution to reduce their emissions. We are, of course, a big number one in hydro, and we continue our efforts to develop more performance-enhanced products for nuclear. A second block and possibility we have to cope with emissions is to do more with less. It's efficiency. And we have programs to improve the efficiency of coal-fired plant that's raising the temperature of the steam cycles. Our best available technology today is at 610, 620 reheat temperature. And we are aiming for going to 700 degrees in the steam cycle by using new alloys. But this needs testing and development, and that should allow us to reach a cycle efficiency of over 50% on a coal-fired power plant. On gas, we have recently announced 61% efficiency on a new adaptation of our turbines. So it's an ongoing effort, produce more power with less fossil fuel. Then when everything is done on technology mix efficiency, the last solution we have is carbon capture and storage. And we have developed a very strong program to come up with solutions in that area. So let's look at carbon capture and storage into more detail. I will first start with a quick video. It's a 3D video that is going to show you what is carbon capture and storage in a nutshell. We will start from a carbon capture ready power plant. That's the power plant you see here. It's a reference 800 megawatt coal-fired boiler. You see the coal yard here. You see the conveyor belt bringing the coal to the burners. You see on the back of this big boiler a steam turbine hall. You see also the switch yard, and then the electricity is exported. You see a cooling tower. What you see also on the back of this power plant is all the air quality control systems. We remove particulate matter. This is an electrostatic precipitator to take care of any dust that we have in the flue gas. You also see equipment to desulfurize the flue gas when need be. What you see also is the chimney that is deported in this case, leaving some space available to install a capture plant. Let me start the video and you will see how we go from capture ready to capture effective. And you will see what we mean with carbon capture and storage. So that's the space we have reserved to capture the CO2. What you do obviously also is study the storage option, and these needs to be validated before you can kickstart your capture operation. What you also do is some preparations on your turbine hall. You have tie-ins to prepare and maybe adapt your turbine for such that you can take steam for the capture unit. You also reserve space in your switch yard to install new transformers. You will need power for compressing the CO2, for instance. And once you decide to go for capture, you can install those new transformers. You don't need to shut down your power plant. You can continue to produce power. And then you start installing your capture equipment. In real life, it's a little bit slower. But let's now look how it operates. You take your flue gas, take it to the absorber column. This is a big washing tower. You're going to wash the flue gas with a solvent, in this case amine solvent, and this washing ensures that you have removed your CO2 from the flue gas. Now you have a rich solution that is carrying the CO2 to a stripper column. That's where you need steam to strip the CO2 of the solution. That solution can be recycled to the absorber. The CO2 then goes to a compression building, where we typically take it to a pressure of around 100 bar, and that is the pressure needed to inject the CO2 in a storage site. What we see here is a convenient storage site that is onshore and very near to the power plant, as we could find in North America. And we inject the CO2 typically at depths between 2,000 and 3,000 meters, where we find sedimentary basins. Those are saline formation, where the sea was present million years ago. It's porous rock. You can inject the CO2 there. It will be trapped by the pores, and it will also dissolve in the saline water that you find at those depths. Eventually, it will mineralize over time. So the longer the CO2 stays there, the safer this storage becomes. About half of the CO2 is permanently trapped after only 10 years in the porous structure. So the longer it stays there, the better. So that's carbon capture and storage in a nutshell. So it's about developing a brand new value chain for the power plants. Now you understand that you may need a chemical engineer, because You're not going only to produce power, you're going to need new science to take care of the CO2 with several technologies, pre-combustion, post-combustion, oxy-fuel. I'm going to detail that in a minute. You need to clean that CO2 stream. You need to compress it, transport it, and then store it. And you have several options for that. So we will need to have the oil and gas industry to help us assess a storage site and monitor, and they have the science to do that. We need geologists to take care of that as well. We will need people to lay pipelines and take care of the transportation, and then we will need very good chemical engineers to cope with the capture. So a new world opening for power production. That's in one slide the effort that Alstom has put to develop capture solutions. But our competitors have put similar efforts, although I still think that we've really went in big with the will to come up with a clear solution. It's a program where we work on coal, lignite, gas, so we want capture solution for all fossil fuel. We work in Europe with pilots, in the US, and we work with a lot of new partners we were not used to. We work with oil and gas industry. You have Total here. We also work with Statoil in Norway. We work with chemical companies like Dow. And we also work with our customers like AEP in the US or Vattenfall in Europe. We also work on second generation technology, and I'm going to detail that also. And we also work after this pilot work, but we are already doing feasibility study and pre-engineering study for taking this to a larger scale, 200 megawatt plus. So it's quite an involved program. We have 300 people permanently employed to develop the technology. I won't have the time to go through all those beautiful pilots, so I have selected a few here. We will look at our development roadmaps for all the solutions, and then I picked those pilots, so you will see a large scale, you will see a second generation, you will see what we do in Norway, because Sasol is involved in that project. You will do a small pilot and here a mid-size validation plant. So that gives you a flavor of what is needed to come up with a credible technology. Let's first start with our capture option and revise what is needed or what is possible technically to capture CO2. The first solution is post-combustion. You have a flue gas after the combustion. Well, you can take the CO2 out of that flue gas, and that's what we call post-combustion. You do this by washing your flue gas with a solvent. I showed you in the video example an amine solution, which is already a solution existing in the industry. We are also developing a chilled ammonia solution where we use carbonates to do the same and wash the CO2 out of the flue gas. That's a solution that has many advantages because you can adapt it to any power plant, also to the industry, and you can pick your size. You are not forced to take all of the flue gas. You can take a slipstream and handle part of it, which makes the technology quite flexible for a progressive ramp-up. The second option we have is oxy-combustion. There you transpose the problem a little bit. You're going to combust your fuel with oxygen. And when doing so, your flue gas is CO2. It's very simple. The trick here is to control the temperature inside the boiler, because if you use pure oxygen, you would get very high temperatures and melt everything down. So what we do is recycle part of the flue gas, mix it with oxygen, and then combust in our boiler. The key here is to produce oxygen in a way that is affordable with the less possible energy. There are big industrial gas companies that can do that for us. And we have here a very reliable and robust solution, potentially applying to new power plants. We have tested it also in retrofit. It's possible to retrofit a boiler to oxy. One of the keys is to make this boiler tight. We also look at the metallurgy inside those boilers to cope with the new atmosphere that you have that is different. It's CO2 and water vapor. And then all the classical air quality control equipment does work on CO2 as well with little adaptations. And then the third option we have is pre-combustion. As the name says, you're going to remove the CO2 before you combust, before you produce the power. And the idea here is to produce hydrogen and burn that hydrogen in a combined cycle turbine. Now, to do that and to produce the hydrogen, you have several steps. And you are utilizing gasification, well known here in South Africa because Sasol does it in Secunda to produce fuels. So when you gasify the coal, you use oxygen or air, but you do a partial combustion. The resulting gas is a synthesis gas, so it's mainly carbon monoxide and hydrogen. Then you have steps to convert this carbon monoxide into carbon dioxide, CO2. Those are shift processes on catalyst, and CO2 with water vapor produce more hydrogen and CO2. You then separate the mixture of hydrogen and CO2 at high pressure. So that's the pre-combustion separation. And you end up with a stream of hydrogen that you then combust in a turbine. Well, it's quite an involved process. The advantage is that it happens at high pressure, so the capture itself is more efficient, but it's at the expense of a high capex. Those are expensive units, and our calculation have shown that it would be quite too much a capex just to produce power. We believe in polygeneration, so gasification to produce chemicals and fuels and electricity. But going through all that expenses just for power is difficult to justify. Those units will be also extremely difficult to operate in terms of flexibility. They need to operate steady state, flat out, not always compatible with energy generation. Plus, you can't retrofit this. This is by default a new installation. So at Alstom, we have concentrated on those solutions which are adaptable to an existing installed base. Now let's look at some roadmaps. Post-combustion first. First solvent we are developing is advanced amine through a partnership with Dow. That shows you a typical development sheet. We start from the lab and pilots, small ones, less than 1 megawatt equivalent. We take it to, and we test here on synthetic gases. We then take the good solvents that we have identified and test them in actual industrial combustion. And we then take to a validation plant where we integrate the process and see how it behaves. And we are currently starting a pilot with EDF. It's in the building phase. We will start up early next year. And then you take the technology to large scale, and we have these projects ongoing with PGE, a main Polish utility. It's in fact the largest lignite-fired coal plant in Europe, 400 megawatts. And we have built there a brand new boiler, 850, and we've built it as capture ready, and we will retrofit and capture about 1/3 of the emissions there in Poland. And it's a project that has received support from the European Union. Just to show you one example is this pilot, intermediate size. So it's a pilot that is still running, and Dow is supplying new solvent formulation. We are testing additives, and we are testing the behavior of those solvents with the various pollutants you may face in a coal-fired boiler. The second roadmap I wanted to show you is about this chilled ammonia process. Now, this roadmap is much more busy because this is a process that has never been used in the industry. Whereas amine are used in the natural gas processing industry, it's well-known technology. This is new. We are using a very simple reaction from ammonium carbonate to ammonium bicarbonate. Now, I spare you the equations because for electrical engineers, I felt this could have been maybe problematic. No. A simple reaction, this is about mineral chemistry. So we think this process will be a lot more robust to the conditions we will see on the back of a power plant. And that's why we have developed it. Also in terms of efficiency, we expect a better performance from those reactions which happen at a lower energy level. So we have validated that at the pilot scale in our labs and test rigs. We have taken it to an industrial stage, testing on actual flue gases in the US and in Sweden. That's an oil-fired auxiliary boiler, which we have used with high sulfur content, and that was extremely useful to validate the technology with high sulfur content. AEP Mountaineer is a test that I'm going to detail, but it was our first integrated capture, transport, and storage unit at a 20 megawatt electrical scale, 100,000 tons of CO2 captured and injected. We are working in Norway with Statoil, and Sasol is part of that test, and I'm going to show you that as well. And we are already taking the technology to the next step, a larger scale, with projects in North America and also Romania. Mountaineer, we are extremely proud of that because we were the first really to integrate the full value chain on the back of a power plant. This is a 1,300 megawatt coal-fired power plant in West Virginia. And we have taken a slipstream, about 2% of the flue gas from that big power plant, and taken it to this installation, where with this bicarbonate reaction, we have separated the CO2 and then compressed and injected. And America is blessed with a lot of saline formations, and it's a big sedimentary basin, North America. And they have a very good storage site just under their feet. So we have injected the CO2 there in two formations at a depth of 2,400 meters for one site, and then another one at 2,800. And it has proven a very also good success on demonstrating the storage at the site. That unit is now shut down. We have obtained all the results we wanted to have. We are building for Statoil another test center in Mongstad at the site of a refinery. The idea is to test side by side this chilled ammonia technology with advanced amine. And it's a competitor of ours that is supplying the advanced amine solution. We will be testing on the flue gas from the refinery that has about 11% CO2. And we will be testing also side by side on a flue gas from a combined heat and power turbine. That flue gas is about 3.5% CO2. So different conditions, and we should learn a lot from that experiment. Again, Sasol has dispatched engineers, and Sasol is part of that test. They've taken a share of the equity in this test together with Shell and Statoil. So commissioning is for early next year. You just can ask me, and I will supply you invitation to come and see it. A very impressive and well-designed center, also for visits. The third roadmap is about oxy-combustion, same principle, from lab to large scale. And Vattenfall was the first pilot that we have started, really, immediately at a 30 megawatt scale, and it was a push-button operation. So to me, Oxy is the easiest one to implement, probably with the least technology hurdles. That's because cryogenics are known. That's because combustion with oxygen, okay, it has its issues, but it's quite easy to solve when you are a good boiler company. At Total in LAC, we have integrated capture with oxy-combustion. Then we have retrofitted an existing 50-year-old boiler to oxy-combustion. It's a gas oxy-combustion. And storage into a depleted natural gas reservoir. So that's the second integrated pilot that we have. Then we still operate our boiler simulation facility where we test new burners compatible with oxy-combustion. And then we are developing, we have several projects at larger scale. I'll show you one of them with Drax in the UK. Now Drax at the Humber site, has the largest coal-fired power plant in Europe. This is coal. This is 4,000 megawatt of installed capacity, about as big as Poland there, but Poland is on lignite. And we have supplied Drax with co-combustion facilities, so they co-combust biomass up to 10% on those 400 megawatts. So a lot of interesting equipment. And we have a project with them to build a new oxy-fired power plant that would be super critical and that would remove 2 million tons of CO2 and store it offshore in the North Sea. So the UK national grid is helping us on the CO2 transport and storage part. We have started detailed engineering on this project, and we are competing for European funding, for which we will have an answer by end of next year. Now, we are also working on second generation technology. Don't try to read this slide. I'm going to try to explain you what this is all about. What we are developing here is an oxy-combustion solution that is totally revolutionary and based on fluidized bed. I don't know if you're familiar with fluidized bed boilers, but it's basically the combustion being done together with solids in a fluidized atmosphere. So we adapt this technology, and we are going to use a metal oxide as an oxygen carrier. So imagine rust. You know what rust is. That is iron oxide. If you contact rust with coal or any carbon-bearing material at high temperature, you're going to have a combustion because carbon is very eager to catch the oxygen. It's very eager to burn. So it will take the oxygen from the iron or any oxide, and you will have a combustion. You will reduce your oxide to elementary metal in that configuration. That combustion obviously produces a pure stream of CO2 as a flue gas. Now you're left with this iron that has been reduced, and you take it to another fluidized bed where you burn it with air. So you produce an oxide again with energy there as well. And you recycle the metal oxide to the first combustor. So it's a back-to-back with two fluidized beds. So quite a daring technology. The key here is to separate oxygen from air at high temperature and carry it with a metal carrier. And that's what we are doing. We have obviously a roadmap for this. We have already validated that technology at the few tenths of kilowatt size, and we are taking it to the prototype level with a prototype at 1 megawatt in Germany and a prototype at 3 megawatt in the US. We are testing two different pathways, one on metal oxides, but one also on calcium carbonates, because carbonates carry also a lot of oxygen, and you can use them in the same way. So the result of this test will tell us which program we want to pursue further and take to a 10 to 50 megawatt size. So those two prototypes are currently in commissioning. Show you one, the one in Germany, in Darmstadt. You see a decent size columns already, and lots of partners around it. We are the lead partner on this, but we work with universities like Chalmers in Sweden that has developed a lot of know-how on metal oxides and metal oxide combustion. Results from pilots. So we have demonstrated the feasibility of integrating capture, transport, storage. We know that we can capture 90% CO2, and I would offer this as maybe a goal for your 19th anniversary. You know, 90% capture for the 19th anniversary, and I don't know, a pilot test we could have here in South Africa. We have also demonstrated we can achieve 99% purity with this stream. Energy penalty is really the key. When we started the development, we were at 30% penalty, so 1/3 of the power produced from the boiler would have to be used to capture and compress the CO2. We are now down to 20% and on our way to 15. Now, the absolute thermodynamic limit is 10%, so we can't do below because we will still need to compress the CO2 and we need energy to capture. There's no way without it. And what we are aiming for is this 15% barrier with the first generation technology. Only chemical looping could take us below this. So we have developed a good base to scale this technology up to pre-commercial and the 200 megawatt level. Let's now look at the cost. And so with this experience on the pilot, with the fact that Alstom sells turnkey power plants, so we know how to integrate, with that know-how, we have come up with a cost study for what CCS would cost in 2015 and including also learning curve aspects. That study is available. We have, in fact, communicated it at the PowerGen Europe early June, and we have a public document available. For those who are interested, we will put it on the website of the Institute, along with those slides. So if you're interested later on, you can have a look. That's a key slide summarizing results. Now, obviously, the study was quite comprehensive. We've studied cost for coal, lignite, gas. We've studied cost in Europe, North America, Far East, with different assumptions. But the base assumptions is a commercial reference plant, so 800 megawatt for coal and 500 megawatt for a combined cycle. So let's look at the pink block here. What you see is levelized cost of electricity expressed in euro per megawatt hour. Just multiply by 10 if you want rand to keep it simple. What we have here in this bar is the cost of electricity for a reference plant. So we are here at 50 euro per megawatt hour produced. That's the CapEx and OpEx component. That's the fuel component of the cost. Now what you see here, this bar is the CO2 capture and storage additionality. So you're going to aggravate the cost by 70% for a first commercial plant in 2015. And you see here the additional fuel due to the efficiency penalty. You see the cost of transport and storage based on an onshore storage with a pipeline of 300 kilometers. Now, with the learning curve assumption we have in the study, this is where we could take the cost by 2030, still a plus 50% increase in the cost of electricity. Now, if you look at the same cost calculation for gas, those are the results. Obviously, on gas, the fuel component is very big. And that is why this additionality looks lower on gas. It's one of the reasons. And you see here the learning effect. So a cost increase of less than 50% is possible. And this is what we would be looking at. Now, this may sound or look horrendous to most of you. What is important is to compare those cost increase with other decarbonized power solutions, because that's where the game is played. And this is the comparison of our carbon capture and storage solution on gas, on coal. We've also done a sensitivity analysis on those costs, and all the basis for this is in the study, and compare this with other decarbonized power generation solutions, nuclear, hydro. You can have a wide range depending on your site, geothermal. You see here onshore wind, offshore wind, solar PV, and CSP, concentrated solar power. What we see is that CCS is in the ballpark. It's in the ballpark from day one, 2015, when we'll be commercial. So it's a solution that is really credible to include in a portfolio of decarbonized power generation. And to us, it's a clear sign that we must start. We must start as soon as possible, because it's not only about renewables, it's renewables and CCS. And as you see, it will be economical if we give a price to decarbonize power as soon as possible. Now, carbon markets. Where are we? Those curves gives you the learning curve, but now expressed in the cost of CO2 avoided. It's higher on gas here, much higher. That's because you have less CO2 in your flue gas, so it's more difficult to recover. You can picture it that way. And it's cheaper to produce CO2 from a rich flue gas. And that's why you have a lower cost here on coal. So it would be about 50, 54, and 73 euro per ton of CO2 when we start in 2015. So obviously the carbon markets are not there, will not be there in 2015. I don't believe that. In Europe, we are at anywhere between 10 and 15 euro per ton. And I don't see a trend that this will accelerate enough to be at those levels in 2015. Now, with the learning, with a carbon market going up, we could hit trigger points somewhere, maybe in 2025, I don't know. But we would be at, we would need this carbon price to be taken at 40, 50 euro as soon as possible. In the meanwhile, we need other finance mechanisms like we have for the renewables, feed-in tariffs, or any other option to cover the economic gap. Am I running over time? Maybe not yet. So quickly about CCS readiness. So that's a growing trend. CCS readiness is building a power plant in such a way that there will be no hindrance to retrofit it to capture and storage later on. We see regulation evolving in Europe, in Australia, UK, but also international finance institutions like the World Bank are thinking of including this CCS readiness in their conditions for financing. On the capture side is relatively easy. Now this slide may appear complex, but what we do is common sense in the layout of the power plant. And then we look at some fittings around the steam turbine, around the air quality control systems. And we make sure it will be easy to retrofit to capture when the time has come and it's decided. This doesn't cost a lot, maybe less than 1% of the capex for a power plant. So there is really no reason why we shouldn't do that. Now, capture readiness is one thing. You need storage readiness. We have a partnership with Schlumberger to offer one-stop shopping for the customers and make an integrated study. But obviously, you need to carefully evaluate those storage sites. Status of deployment. That's a picture extracted from the data from the Global Carbon Capture and Storage Institute. And it shows you those large-scale projects above 100 megawatts. So we have a lot going on in terms of development in the US, in Europe, even in China, Australia. On several technologies, they are all represented. There is already funding announced in Europe from the DOE in the US. But let's see what is really happening in terms of investment decisions. Out of those 78, we have 6 already operating, and some have started, one in 96 even. Out of those 6, you have 2 operating for tax avoidance reasons in Norway. These are the Sleipner and Snøhvit projects, and they are storing several millions of tons of CO2 per year. You have other projects for enhanced oil recovery. When you inject CO2 in an oil field, you will cause a swelling of the oil that is present, and you can recover from 5 to 15% more out of your oil field. So that's definitely a very good business model to start carbon capture and storage. But when we look at the new projects in execution, we only find 6 having received an investment decision. Out of those 6, 5 are for enhanced oil recovery, and we have only 3 in power. So we would expect a little bit more action. The industry is ready, projects are there, but the finance is quite uncertain, the policy environment as well. So I don't feel we are on the right tracks to meet the targets set by the Carbon Sequestration Leadership Forum of having 100 plants up and running by 2020. So the barriers, the main ones, technically I think we will solve the problems. I see no issue, except for a careful assessment of those storage sites. That's a big effort for which we will tap into precious resources from the oil and gas industry, precious exploration resources, which they rather dedicate on oil, obviously. Regulatory, it's about the ownership of those storage sites, it's about their control, monitoring, verification, and it's about also the liabilities and the handover of a storage site when operations are finished. So all this needs careful thinking and progress. And then the last hurdle is really finance. As I said, we need dedicated finance. I'm a strong believer that we need to put a price on decarbonized power and then let the market choose what they want in terms of solution. But when that price is given, I think we will see projects taking off, and I'm convinced that CCS is competitive with any other solution. So, policy arena, COP17. Those are my last slides. Very aggressive targets here in South Africa. So the most aggressive worldwide, in fact. The intention is certainly there. What we need, of course, is a strong international support to make it happen, international finance. And we lack of a clear definition from the COP as to what those mechanisms will be. To have a successful climate mitigation action here in South Africa, I believe we need to start with the energy sector and the industry sector. And you have two giants here with Sasol and Eskom. They are both motivated. I know that because I talk to them. But they will need regulation, they will need finance, and they will need a crucial international effort also to support this deployment. If we look at the COP16, what we lack since Copenhagen is really implementation of decision, especially on the funding. We had those famous, what was it, $20 billion to be spent by 2012. We don't know where that budget has to come from. We don't know by which mechanism it will be dispatched. And there are a lot of things we don't know, and we are in 2011. We had also 100 billion pledged by 2020, and same, we don't know how this is going to be disbursed, etc. So really the implementation now, it's high time to make those decisions, make decisions also on the adaptation fund, so, and also clarify what is going to become of Kyoto, what do we keep from those carbon market deployment goals. That's my last slide on the possible outcome of COP17, what we would be looking for. So a framework to disburse funds, decision on technology transfer and the mechanism associated with that, decision on adaptation framework and funding, Kyoto Protocol, how we continue. And then for CCS, alas, I have little hope that progress will be made. A big target would be to have the CCS included as a technology to apply for the CDM, the Clean Development Mechanism. It's a mechanism where you can recover money from the carbon market in Europe for developing carbon-free projects. Today, the CCS methodology is not accepted as a CDM project. So you cannot get money for storing carbon. So a lot has to be done on proper definition of what we mean, on the monitoring, etc. As soon as you store carbon underground and you get money for it, it's like storing money in a safe underground. So one can understand that it's a delicate issue, but it has to be really tackled in full force. Not sure it will be really on the agenda of the COP17, we will see. I just hope so. So that's it for my presentation. I thank you for your attention, and I'm at your disposal for any question.
Ladies and gentlemen, I think it's a wonderful presentation that has given us a lot of food for thought. In South Africa, we're blessed with a lot of coal deposits, which we will have to use to generate power. However, we have to find ways and means of generating that power using coal in a responsible manner. I think Philippe has given us a lot of food for thought. As he said, he's inviting questions. If we can have some questions or comments from the audience, I'm not sure how we can handle that. If we have some roving mics that we could use for that.
There is a microphone.
There's a gentleman there.
Islam. My name is Dave Collins. You work across all the energy sources, nuclear, coal, etc. We know that the Japanese are now very nervous about future nuclear. We know the Germans are pulling out of nuclear. Even South Africa has said we may delay by a year or two of nuclear. How do you see the gap that could be left by people pulling out of nuclear? Will it go to coal with CCS, or will it go to renewables? How do you see that dynamic working out?
Well, I think the answer is quite clear. What we see when you open your eyes is that gas is there. And gas has a strong fit with renewable penetration. And we've seen a big wave of new gas discoveries, those famous shale gas that give hope in the US for endless provisions. They also have the potential to reduce emissions, because gas, for the same amount of gigawatt hour, is emitting about half of the CO2 compared to coal. So it sounds like this is a good solution because gas is flexible, to accommodate the penetration of renewables, at the same time diminish the emissions. And that's where the world is looking. We see new pipelines coming in Germany, lots of pipeline projects to bring gas from Eastern Europe into Europe. We see shale gas projects everywhere. So that, I think, is the first answer that governments and energy decision makers have on the back of their minds. I think it's a short-term view, because gas is not going to solve this climate problem at all. It's half of the emissions nice. If you replace instantaneously all the gas-fired power plants in Europe or in the US, you achieve about 30% emission reduction. That's nice, okay, I buy this. But it's 80% that we want. You've looked at the 450 ppm trajectory. So I think we need nuclear, we need renewables, we certainly need gas, and we need CCS. I mean, there's no way we are going to escape this equation. It's just a matter for things to progress in the understanding of our decision makers. We're not there yet. So.
Good. Any other questions?
My name is Chris Gillen from EU Publishers.
There's a mic.
Chris Gillen from EU Publishers. I went to a lecture the other night by a quite well-known, currently a nuclear physicist in South Africa, called Dr. Kelvin Kemp. He spent the entire lecture explaining that man-made global warming is a myth. And can you give your perception? I read articles and people are saying these things, apparently credible people, but can you give us your view on this CO2 warming, man-made warming denialism that we are seeing in South Africa, and I think in other countries too? What is your response to this?
Very good. That's a very good question. My response to this is first that we know that CO2 is accumulating in the atmosphere, and that the CO2 accumulating in the atmosphere is from anthropic origin. They could do that with isotope tracing. So those molecules, you could look at them, they come from human activity, and their accumulation comes from human activity. Now you have thousands of scientists that have established the correlation between this CO2 and the Earth's surface temperature increase. What we don't know is how much this will cause in terms of climate change. But we know that there is a correlation. We don't know how strong, exactly how much ppm, and that's why I showed you those probabilities. So this we don't know. There is another effect besides global warming, is ocean acidification. I've not talked about it, but it's also one of those nice side benefits we get from CO2 increase, is that ocean is becoming more and more acid. And we see big damage in coral reef. And some people and some scientists raise their voice and say this is even worse than climate change in terms of what the sea will be providing in the nature in the sea, and the sea as a food reserve for humanity. So with those two problems, I think we have no time to lose. It's an essential precaution we have to take and take care of that CO2. That's all I can offer. I'm not a climate scientist.
Thank you.
I just wanted to ask a very simple question, a very simple answer. I'm just an electrical engineer. If we assume exactly until now that all the electrical energy that's being produced and currently being produced is, let's say, produced by coal. Now, to build one of these carbon capture plants, you actually need lots of steel and lots of concrete, which are produced by electrical energy, which is being produced as a result of CO2. And the compressors to get the CO2 to 100 bar, etc., are going to use a lot of electrical energy, which also comes at the expense of CO2. So the question is, how much CO2 is released into the atmosphere, or has been released into the atmosphere, to store X kilograms of CO2 underground? So it's a CO2 balance.
No. What I've showed you in terms of cost and energy penalty is an all-included number. So it includes, obviously, the energy you spend to compress and store the CO2, to capture it and everything. It doesn't include the CO2 emissions for steel and cement additional that you would need. Now that's a more complex life cycle analysis question, which we obviously will tackle. But compared to the global emissions of a power plant, we're talking here about 7 million tons per year. This will be peanuts. We've looked at steel availability, because it was one of my questions. Will we have enough steel? And when I look at the global effort to develop carbon capture and storage, it's peanuts compared to the building effort and the materials that are required there just to expand our cities into mega cities worldwide. So that's also not a problem, apparently.
Great. If we can just have two last questions. Paul here, please. The person here.
I wanted to ask two simple questions. One is that since you're doing business with Eskom, are you aware if Kusile or NWP carbon capture ready? And number two is that is there any geotech studies that have been done to ensure that we do have the capabilities for the storage of carbon?
Okay. You know the game Who Wants to Win Millions? You have this option that you can call on someone to answer a question. So I'm going to use that option, because I have my friend Barry McCall from Eskom here in the room. If you could tell us a little bit, Barry, what is being done at Medupi and Kusile, maybe the microphone.
Barry McCall, I'm the research manager at Eskom. As it stands at the moment, Medupi is not carbon capture ready. Kusile is carbon capture storage ready. Fundamentally, what we've done at Kusile, or are doing at Kusile, is we're making the provision for the electrical supply that Philippe mentioned, making space for the plant. We're also reducing the particulate emissions from the station. Particulates in that scrubbing process that we mentioned can start the process. We're also reducing the SOx emissions from the plant, because the SOx can poison the catalysts involved. So that's been done at Kusile, not at the field. In terms of the geotech studies that have been done, there's a center in South Africa called the South African Center for Carbon Capture and Storage. That, along with other partners, Eskom and Sasol, funded a carbon storage atlas, a document that was produced last year. And that has identified certain areas in South Africa that are reasonably good for carbon capture and storage, or for the storage component. And we're busy exploring, as we speak, those areas of the country geologically. So we've got the Council for Geoscience on board, Petro SA, looking at the rock formations on the ground with the intention of having an injection experiment by 2016 in South Africa.
Thank you, President. Alan Paul from Africa Biofuel. What are the factors driving the pricing of carbon credits, and what is your scenario projection for the direction of those carbon prices?
Okay. Good question. Today, the only comprehensive carbon market we have is the European trading schemes. We have attempts in the US. California is going to start their scheme. There was the RIGI regional test also in the US that is a little bit shaky right now. China is going to experiment with carbon market. But the fundamentals behind and supporting a carbon price is energy consumption. The way the European carbon market functions is through allocation. So until 2012, it's based on grandfathering. So you receive free allowances that are compatible with what you have been historically emitting on a yearly basis. So now, if you are growing your activity, you will emit more. You have to purchase carbon on the market. If your activity is going down or you have put efficient technology, your emission go down and you can sell your carbon to those who have been less virtuous as you have been. That's the principle of the carbon market. So the drivers is growth of energy demand. That drives the price of the carbon up and in turn triggers technology to be developed to reduce these carbon emissions. What we have, however, as a problem in Europe is that we have this carbon market, but it's not the single tool that Europe is using to cope with reducing the carbon emission. They also enforce renewables. So they want to push renewables. They force member states, and they want to have 20% renewable by 2020. They've now issued a directive for efficiency. Now, all this is, of course, going to have an impact on the emissions, the global emissions. So that, in turn, is going to have a downward pressure on the carbon price. So it's quite complex. If you want the carbon market only, you can do that, but you make, but then you do that with an auctioning process, and you make sure this price remains high. But if you combine several measures, you can have undesired effect, and that's what we are seeing in Europe, with a price that is quite low, also due to the crisis that has really put a downward pressure on the price. Now, from 2013, we will have an auctioning process. So every emitter will have to purchase their emission permits in an auction. And there are discussions maybe to set up a carbon bank that will control the price of the carbon by withdrawing permits from the market. Would be a good way, set aside technique, so to control and make sure this price doesn't collapse overnight. So all those things are still in discussion. I think we are heading in Europe for a stronger carbon market if those ideas are being implemented, but we will see. So it's a complex system. But,
yeah, it's a very interesting question, Philippe, because Philippe and I visited the landfill conversion project in Durban, where you're converting methane to energy, electrical energy, and they are actually flaring some of the gas. However, they expressed very serious concern about the bureaucracy in getting those credits. So the carbon market really still has to sort its house out. I think if there's any last really pressing question, then I wouldn't mind closing the question and answer session now. Great, thanks, thanks, ladies and gentlemen. If we could just ask our Deputy President, Mr. Mike Carey, to propose a vote of thanks to our speaker.
Vice Chancellor, staff, students of the University of Witwatersrand, members of the South African Institute of Electrical Engineers, ladies and gentlemen. It's indeed my pleasure to propose this vote of thanks to Philippe. think everyone knows the population of this earth is growing. At the same time, the amount of energy consumed per capita is growing. So obviously we need new power sources all the time. Philippe has given us a good sketch of what is happening and where the power is coming from. Unfortunately, the non-fossil fuel sources of power are still fairly in their infancy in terms of development. It's also showed us the risks of temperatures rising above 2 degrees. And it's maybe a topic for another day. Just the water is a major problem. People seem to close their eyes to, as I did in 2008 in this country with the blackouts. He's also sketched a number of solutions to the carbon, the gases going into the atmosphere. To be a successful lecture for this prestigious Bernard Price Memorial Lecture, it has to be topical, interesting and relevant. And I'm sure all of you will agree that Philippe Pradelink made this lecture topical, interesting and relevant. And I'd like to ask him to come forward and accept a gift from the Institute for his presentation.
Thank you very much, Mark, for that. And it remains for me now to thank the Vice Chancellor, Professor Loyiso Noonga, and the Wits University for the use of their facilities. The relationship between the Institute and Wits is a long-standing one. And as I said earlier, we always feel welcome at this university. And we spend a lot of time collaborating with the Faculty of Engineering and Built Environment, especially the School of Electrical and Information Engineering. We, as always, we're very thankful for your hospitality, Prof. Otherwise, ladies and gentlemen, I think it's been a long meeting, and the speaker tried to, if I can try to illustrate to you, he arrived on Monday and immediately went to Durban. He presented his lecture there after a tiring visit to that plant in Durban. And then thereafter, he was whisked off to Cape Town, and he visited the Palmeet pump storage scheme in Cape Town, which is an ESCOM project, and he presented his lecture at the center there. He was then quickly whisked off to George, where he presented his lecture. We didn't want to leave the retirees out of this lecture. I think they're very important to us. And we've just come back this morning from George, and hence this lecture tonight. I'm very happy that Alstom has made Philippe available to us to share, as Philippe indicated, the information and knowledge that they have gleaned from the research and development, spending hundreds of millions of euros per year in doing research. Unfortunately, some of this research that companies do, it's never made available to the public. And Alstom has done exactly that today, and we're very thankful for that. Ladies and gentlemen, otherwise, it leaves me with the last duty of inviting you to come and enjoy refreshments on the foyer with us tonight. And the last task I have to do is to declare this meeting closed. Thank you.